Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'll be answering question 14A of the 2020 New South Wales HSC Extension 1 exam. So this question got a bit of a reputation as being quite a tricky one, and soon after the exam was sat last year, I had some students get in touch just mentioning that they found this one to be a bit of a brain teaser. So I've had a student send it through to me on TickBoom asking me to work my way through. So I'll do my best to kind of work out a solution that hopefully is easy enough to follow along with. If you do find my explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, be sure to subscribe to my channel so that you can stay in the loop. So if we take a look at this question, it's got 4 parts. Each part is worth 2 marks. The first part says to use the identity 1 plus x to the 2n equals 1 plus x to the n times 1 plus x to the n to show that 2ncn equals nc0 squared plus nc1 squared and so on up to ncn squared. Part 2 then tells us that a club has 2n members with n women and n men. A group consisting of an even number of members is chosen with the number of men equal to the number of women. Show giving reasons that the number of ways to do this is 2ncn. Part 3 then says from the group chosen in part 2, one of the men and one of the women are selected as leaders. Show giving reasons that the number of ways to choose the even number of people and then the leaders is 1 squared nc1 squared plus 2 squared nc2 squared and so on, all the way up to n squared ncn squared. And then finally, in part 4, we're told that the process is now reversed so that the leaders, 1 man and 1 woman, are chosen first. The rest of the group is then selected, still made up of an equal number of women and men. By considering this reverse process and using part 2, find a simple expression for the sum in part 3. So you can see why a lot of students would have potentially found this one a bit difficult. There's quite a lot to it, and combinatorial questions have a bit of a reputation for being difficult. There's not really a lot of formulas that you can make use of. It's not a kind of topic where you can just methodically and mindlessly apply formulas to work out answers. You always need to be thinking. I remember in my degree, I took a subject called combinatorial probability, and my memory is that was one of the hardest subjects of my degree, and it never really gets easy. But what we can do, I think there is a way to tackle this question that isn't too I guess, beyond reach. I think it is quite a feasible question to be able to tackle. So I think the key is really just staying calm and kind of slowly and methodically applying what you know to kind of get to these results. Okay, so for part 1, we're being told to use this identity 1 plus x to the 2n equals 1 plus x to the n times 1 plus x to the n. So all that's been done here is the 2n's just been written out one at a time to show that 2ncn is equal to nc0 squared plus nc1 squared plus and so on, all the way up to ncn squared. And I've used this kind of C notation rather than the brackets notation, just because that's kind of the old habit. It's the way I learned. The exact notation you use won't affect the marks you get. I've just always found it easier to think about NCR and NPR, so I always just found this notation a bit more intuitive. But when you're faced with questions like this, so where you're given something written in 2 forms and asked to prove a combinatorial result, what you want to think about is the binomial expansion. And I actually had a student send through a different question that required the exact same technique. So I might share a link to that because that would also be worth looking at for a bit more practice on these kinds of questions. But the binomial expansion allows us to write 1 plus x to the n in expanded form, which would be the sum from k equals 0 to n of nck x to the k. And what we'll do is we'll use this technique to expand both the left-hand side and the right-hand side, and we'll equate coefficients, and hopefully through that process end up with this result. So if we start with the left-hand side, we can write 1 plus x to the 2n is equal to, and here, because we've got 2n in the exponent, wherever we see n here, we'll just write 2n. So we'll get 2nc naught x to the naught plus 2nc1 x to the 1, and so on. And I might just write the middle item 2ncn x to the n, and so on, and you get 2nc2n x to the 2n. And the reason I wanted to write this middle item is because with our x to the n item, the coefficient is 2ncn, which is what's over here in what we're trying to show. So we know that the item that we want to find the coefficients of is x to the n. So that's what we'll be focused on when we're expanding the right-hand side. So if we now look at the right-hand side, 1 plus x to the n times 1 plus x to the n can be written as nc naught x to the naught plus nc1 x to the 1, and so on. I might write the last two items, so ncn minus 1 x to the n minus 1 plus ncn x to the n multiplied by itself, because it's the same thing multiplied, so nc naught x to the naught plus nc1 x to the 1, and so on, to ncn minus 1 x to the n minus 1 plus ncn x to the n. And technically what we need to do is multiply each item by every other item to expand this. But because we're only focused on what's in front of x to the n, we only rarely need to write out those items that are going to result after multiplication in x to the n. So, you know, we'll have a whole bunch of items, and then we'll get up to nc naught x to the naught. It'll eventually get multiplied by ncn x to the n. And I'm interested in that item because naught plus n will equal n. And then there'll be a whole bunch of other things, and then eventually I'll get to nc1 x to the 1 being multiplied by ncn minus 1 x to the n minus 1. And again, I'm interested in that because 1 plus n minus 1 gets me x to the n. That'll just keep going, looping through, and then I'll get ncn minus 1 x to the n minus 1 times nc1 x to the 1, and so on. And then I'll get ncn x to the n times nc naught x to the naught, and whatever else. And so now what I can do, knowing that each of these, when they're multiplied, will get x to the n, I can now write this as whatever I get plus, in brackets, nc naught ncn plus nc1 ncn minus 1, and so on, plus ncn minus 1 nc1 plus ncn nc naught x to the n, and then, you know, plus whatever else we get. We only really care about this. So now we can equate coefficients. To then say 2ncn must be equal to nc naught ncn plus nc1 ncn minus 1, and so on, plus ncn minus 1 nc1 plus ncn nc naught. And we're kind of close here. We just need all of these squares. But if we note that NCR can be written as NCN minus R because of the symmetry of Pascal's triangle, basically, then we can see what we end up with, because then we can conclude that 2NCN is equal to NC naught times NCN minus N, which would be another NC naught, so that's squared, plus NC1 times NCN minus N minus 1, which would just end up with NC1, so that's also squared, and so on. And you see that this result gets us everything squared. NCN minus 1 times NCN minus 1, so that's squared, and then NCN times NCN minus 0, or NCN squared. And that's the result. So that's what we were required to show. So that's how you can tackle this first part. It's basically the binomial expansion and then equating coefficients. And you just got to be really careful here in doing your expansion to kind of make sure you end up with the right things that get you the x to the n. So hopefully that was all clear. So now I'll look at part 2. So part 2 is saying that we're selecting from n women and n men. So we'll always have an even number of people, and it'll be the same number of women as men. So if we look at all of our cases, we could have 0 women and 0 men. That could be one outcome. So if we think about the number of ways we could do that, how can we pick 0 women from n and then 0 men from n? Well, that would be first the women. We'd take NC naught to get our women, and then we'd multiply that by NC naught to get our men. So that's just going to be NC naught squared. We could have 1 woman and 1 man. That's another way to, you'll end up with an even number of people and an equal men and women. So similarly, we could do that. We could pick 1 woman from n in NC1 ways, and then 1 man from n in NC1 ways. So that's also going to give us something squared, NC1 squared. And I might just write out 2 women and 2 men. It's going to be NC2 times NC2, so that's NC2 squared, and hopefully you see the pattern. So if we have n women that we're picking and n men that we're picking from the n available of each, we'd have NCN times NCN, which would be NCN squared. So therefore, the number of ways that we can do this, that we can pick from n women and n men so that we have an even number of people and equal men and women, is equal to NC naught squared plus NC1 squared plus, just adding all these up, NC2 squared and so on, up to NCN squared. And it's at this point that we see why we went to all the effort we did in part 1, because we've just shown that the sum of all these items squared is equal to 2NCN. So that's 2NCN from part 1. And that's what we were required to show. We were being asked to show that the number of ways to make these selections is 2NCN. So that's part 2 done. I think it really was just, I guess, applying the result from part 1. All the hard work was done in part 1 to then allow us to make use of it in this part 2. So that now brings us to part 3. Now the facts of part 3 were that we're going to do the same thing, but with an extra step. So we've got same as 2, selecting from n women and n men, and having an even number of people, equal women, equal men. And we'd have a leader, so 1 woman leader and 1 man leader. So how can we do this? Again, we can work through the cases. So if we think about 0 women plus 0 men. In that case, this is not applicable because if we need at least one woman leader and one man leader, then you've got to be picking at least one. So now if we're doing one woman and one man, well, like before, we'll pick the woman. There's NC1 ways we can do that. And then once we've got that woman, there's one C1 way to choose the leader. It's basically one way because there's only one to pick from. And then same with the men, NC1 ways to pick the man times 1C1 ways to make that man the leader. So I'll just write that as NC1 squared times 1C1 squared. Now if we look at 2 women and 2 men, similar to before, we'll have NC2 ways to pick the women, and this time we'll have 2C1 ways to pick a leader. So one woman leader from those 2 women we've just picked. And then same with the men, there'll be NC2 ways to pick the 2 men from the N, and then 2C1 ways to pick the 1 leader from those 2. So that we can write as NC2 squared times 2C1 squared. Hopefully you see the pattern. So if we have N women and N men, we'll have NCN ways to pick the women times NC1 ways to pick the leader. And then for the men, NCN ways, and then NC1 ways to pick the leader. So that can be written as NCN squared times NC1 squared. So therefore, the number of ways is equal to NC1 squared times 1C1 squared plus NC2 squared times 2C1 squared and so on, plus NCN squared times NC1 squared. So now something we can note, and maybe I'll just have to, maybe I'll turn the page just to have a bit more space, but something we can note here is that KC1, or any combination where it's 1 at the bottom, we can write that as K factorial times 1 factorial K minus 1 factorial. And that, therefore, is K times K minus 1 factorial on K minus 1 factorial. And these cancel, and it's just K. So now every time we get our 1C1 or 2C1 or NC1, we can just replace that with 1, 2, N, because each of these will just be the value up here. So therefore, the number of ways can now be written as NC1 squared times 1 squared plus NC2 squared times 2 squared, and so on, up to NCN squared times N squared. And actually, the result we were trying to show just had these reversed. So that's 1 squared times NC1 squared plus 2 squared times NC2 squared, and so on, up to N squared times NCN squared as required. So that's how to tackle part 3. I think it was really just kind of taking the same approach as part 2, but then adding on this extra step of picking the leader from the number of people. See how this number here kind of translates up here each time. And that's because we're picking a certain number of people and then we're picking 1 from that. And then knowing that you can simplify that is how we can get to the ultimate result that we were being asked to show. So that leads us to part 4, where they've said it's basically the same as part 3, but reversed. So what we do is we pick the leader first and then we pick everyone else. So in that case, there'd be n ways to pick the woman leader, and then there'd be n minus 1 left, n minus 1 women left to choose. And it's the same with the men, n ways to pick the man leader, and then you'd be left with n minus 1 men left to choose from. So we were told in the question to think about part 2, because note that from part 2 there are, so from part 2 we can say there are, and if we go back to part 2, there are 2 NCN ways to pick n women and n men. So we showed in part 2 that if you've got n women and n men that you're trying to choose, there's 2 NCN ways to do that. So therefore, if we're trying to pick n minus 1 women and n minus 1 men after we've picked our leader, then that means there are 2, and I'll just insert n minus 1, c n minus 1. So wherever there was n here, we'll just put n minus 1 ways to pick n minus 1 women and n minus 1 men. So therefore, the number of ways to do what we want to do in this reversed approach, it would be equal to n ways to pick our woman leader times n ways to pick our man leader times 2n minus 1 c n minus 1 ways to pick the n minus 1 men and women who are left over. So that is n squared times 2n minus 2 cn minus 1. So therefore, because what we did in part 3, picking a woman leader and a man leader, and then or actually picking a certain number of men and women and then a leader from them, because that is effectively equivalent to picking the same amount of people, just picking the leader first, the amount of ways to do that should be equal. So therefore, the number of ways to do part 3, this 1 squared nc1 squared plus 2 squared nc2 squared, and so on, up to n squared ncn squared, that must be equal to this, n squared 2n minus 2 cn minus 1. They must be equivalent because you're effectively picking out the same number of people from the starting point of n women and n men with one leader from each. The fact that you've done it in the reverse order doesn't change the number of ways you could do it. So that's part 4. That kind of is how we've written this simpler version of the result in part 3, making use of our result in part 2 as the question guided us to doing. So there you have it. That's how you do that question. I mean, yeah, quite a lot to it. I think to tackle this and get all the marks, you do need to be very comfortable with your combinatorics. I mean, in the end, it's not like it was mountains and mountains of working required. It was really just having the deepness of the understanding, particularly with part 1 and this binomial expansion, just kind of working methodically through that. And then kind of having the I guess, ability to recognize that this result now can be made use of in part 2. So kind of working through all the cases, getting a result that we then link to part 1. And then part 3 and part 4 were just minor tweaks on part 2. So just kind of each time, you know, building upon what we'd just done before. So from that perspective, it's quite a nice question because it's guiding you through to get you to a result that, I mean, you wouldn't really think of this result out of nowhere, but once you're guided through it, you can see it's quite an interesting result to know. So hopefully you found that helpful. Again, if this explanation did help, please give the video a like. That's one way you can let me know. And again, if you're the type of person who wants to keep your finger on the pulse with the kinds of questions that other students are struggling with, then be sure to subscribe to my channel, and that way you can keep in the loop. So yeah, hopefully you found all that helpful, and tick boom.